let me proceed with a little bit of background. So, like Martin said, I'm an associate professor at Stony Brook University in Long Island, New York. I work on a number of research areas, all related to the web. So I work on online tracking, and I have a talk later today related to online tracking, which I hope you can attend. We work on DNS security with my students. We work on web application fingerprinting, so effectively understanding how applications can be fingerprinted online and who does it and how can we defend against it if it's unwanted. Mobile browser security, so how do browsers on your phone behave differently than browsers on your laptop or desktop computers. Attack surface reduction, so web applications, like all other software, is growing larger and larger. So how can we actually shrink it so that we keep all the features that we want and get rid of all the features that we don't want, including the vulnerabilities in the features that we don't want. And then honeypots and deception. So how can we use honeypots technology to protect webs to increase web security? And anti-bot technologies, right? So how can we differentiate between benign regular users on your web application versus a benign and versus a malicious one? All right. So as you may know, there is actually quite a bit of traffic on the web that is bot related. So if you see here, this slide, according to this anti-bot company, less than 60% of the traffic online is human related. So the rest is all bot related. So let's get on the same page regarding what is a bot, right? So web bots are effectively just programs that people have written that can act as a user in terms of browsing, fetching websites, fetching resources, navigating to different places. And so we actually rely quite a bit on benign web bots, right? So whenever you use a search engine, you're relying on that search engine having an army of web bots that constantly go on the internet, crawl, index, so that they can give you the right results when you search for them. When you paste a link on a social network, nowadays you're likely going to get some sort of preview of that link. And what that means is that a crawler just went out, fetched that page, and generated a preview so that you can see it before you post it, and your followers or your people on or your collaborators can see it when they receive your message. And on the security perspective, we also rely quite a bit on this for detecting any sort of bad thing online, right? So phishing sites, malware, large security companies are, again, operating their own large armies of crawlers and bots that are going from website to website and flagging things that look suspicious, and then they end up in block lists and so on, right? But pretty much the same technologies and the same flexibility that makes benign bots so powerful can also be turned against us and against the owners of web applications. So we have armies of malicious bots that are constantly crawling the web, searching for victims to abuse, right? And in terms of abuse, we have quite a number of things. So we have unwanted scraping. So you can have bots that are scraping sites, not to necessarily index them, right, but to steal information, steal their inventory, their pricing, right, potentially set up clones of that sites and steal some traffic away from the original site. We have bots that are brute forcing credentials, so finding login forms and just hammering them with stolen credentials from other sites and from other compromises. Searching and stealing backup and configuration files, so effectively finding files that the developer should not have left where they left them. And finally, discovering that a web application is vulnerable to something, right? And then the bot proceeding to exploit that vulnerability, potentially uploading a backdoor, and then the owner of that bot can use that compromised box or can sell it to someone else who will then use it. So let's try to differentiate between benign web bots and malicious web bots. So benign web bots, one of their characteristics is that they announce themselves, right? So if you get a benign bot on your web application and you look at the user agent, it will tell you, hey, I'm Google bot or I am Bing bot, right? And of course, we understand that the user agent is something that is completely coming from the client side. So an attacker can quite equally claim to be a Google bot or a Bing bot or a Facebook bot, right? So that in itself is not enough for us to distinguish between benign and malicious bots. However, large companies, what they do is that they actually announce their subnets from which their crawlers operate. So these are in well-defined IP ranges. So you can actually look for every client that's coming to you and says, I am a Google bot, I'm a Bing bot, I am something else. Again, for a large enough company, you can look up whether the IP address of that client is coming from an expected subnet. Okay, and if it doesn't, it means that someone is most likely faking the user agent, right? And another complementary strategy is effectively a reverse DNS, where you take the IP address of someone claiming to be Google bot or Bing bot or something else, you reverse DNS it, and then you see whether the reverse DNS domain now falls in the right label space, as you would expect it. So you can see on the bottom of the slide here, we have two user agents, we have two hosts that are both claiming to be Google bot. The top one, when we reverse DNS it, so we take the IP address from our logs and we reverse DNS it, we will get something ending in .googlebot.com, and you can then look at Google's documentation and discover that this is indeed appropriate, okay? But for the other one, you can actually see that this is falling in some sort of residential ISP network. So highly, highly unlikely, of course, that Google is placing their bots in residential ISPs. So this is clearly someone who's pretending to be Google bot, trying to pretty much evade any blocking, server-side blocking, because the idea is that websites will be very leery of blocking Google bots or Bing bots or other bots. So if you see Google bot, they'll just let you keep going as opposed to stopping you early if you are a user who's sending the same number of requests at the same frequency, right? So that's the idea. So this is kind of straightforward, right? If a malicious web bot is trying to pretend to be a benign web bot, we have ways of differentiating that, at least for the large companies. The second strategy is a little bit more complicated, right? So here you have a malicious bot that is pretending to be a regular user, right? So again, the bot now, instead of changing the user agent of its program to Bing bot, now it will say that it is the latest version of Mozilla Firefox or the latest version of Brave, right? So effectively, the attackers have a number of things available to them, all of them controlled at the client side, right? So they can spoof user agents to be whatever they want it to be. They can simulate user actions by scrolling, by tapping, by clicking, right? They can go low and slow. They don't have to hammer your server with thousands of requests at once. And they can use proxy servers to locate themselves from wherever it is that you're expecting traffic. So I could very well be operating my malicious bots at the public cloud, but I can buy residential proxy access from various companies and now appear to you as if I'm coming from a typical ISP network. All right. So the defenses of this, how do we actually find these bots that do this, is quite more open-ended, right? So we can use anomaly detection. So we can look at the timing of requests and say, okay, this user who claims to be a user is moving too fast through my site, right? And we can sort of decide that this is some sort of anomaly, and we can choose to take some actions against this specific IP address, right? We have the types of requests. So a common pattern of some types of bots that they're trying to be more lightweight. So they will, excuse me, they will not load images or CSS files or JavaScript because they don't really need it, right? They just want to scrape you and they want to go from page to page. So if you actually see a chunk of the requests that should be there on your server not being there, then you can again deduce that something fishy is going on, right? And so we can then say, okay, when we're a little bit suspicious, let's throw a CAPTCHA at someone. But of course, you understand that you cannot overdo this, right? So you cannot be exposing 90% of your users to CAPTCHAs, right? Because you're suspicious. So this will typically websites, particularly the ones that are afraid of losing their users, the users about to purchase something, they will err on the side of caution and let more bots go through rather than have more users click through CAPTCHAs, right? And the rest is open-ended pretty much. That's what we'll talk about today. And you can see here an example in this picture from earlier this year. So I have 3 visitors on my personal site that they claim to be a recent version of Chrome running on Windows 10. Okay, so far so good. But if you look at the screen resolution, you will see that this is an 800 by 600, right? So this is clearly highly unlikely, right? That you have a 2021 machine running the most recent version of Chrome and Windows, but it's operating a resolution that is from 15 or 20 years ago. So this, you can see that an attacker here has tried to hide certain parts of himself, but hasn't done so comprehensively. So this brings us a little bit now to the problem that we're trying to solve. So we are interested in building systems for detecting malicious bots, right? But in order to train the systems, in order to evaluate the systems, we actually need data sets of malicious bots, right? So we can actually say, okay, look, we can detect our known bots, right? But of course, in order to procure data sets of malicious bots, you need systems for malicious bots, right? So you have the circular dependency that we somehow need to break, right? And in academia, at least, a lot of my colleagues did in the past is that they looked at the web server logs that they had access to, and they just manually went through them. And they said, okay, this is a bot, this is not a bot, this is a good bot, this is a bad bot. But of course, you can understand that this is highly error prone, right? So the question that we set out to answer is, can we actually curate a bot-only data set that doesn't rely on us being particularly good in labeling and differentiating, right, between benign users and malicious or benign bots. So we want for this data set to allow us to, as I mentioned, differentiate between good bots and bad bots. We want to understand the activities of bad bots. So what is it that they do when they attack your website? We want to be able to actually to uncover the real identity. So I see that a bot has come to my website, it's claiming to be Mozilla Firefox, but what is it really, right? And then map and study trends of bot activity over time. So we set out and we built this system that we call Aristeos. And Aristeos is a minor god in Greek mythology who was the protector of beekeepers. And so our system is pretty much relying on this idea of using deception for security. And specifically, the system is providing a flexible deployment and management of honey sites. So what are honey sites? Honey sites are fully functional web applications that we have augmented with state-of-the-art fingerprinting techniques. And they only exist in order to be attacked, right? So these are real websites. They are really running on real web servers with real web application engines, but they don't have any benign users, right? They're not supposed to, okay? And so we deploy these honey sites, and of course, I'll give you much more information. And then we have centralized server that pulls logs from these every single day, and then we can study these logs and understand what it is that's happening. And because these, right, are not meant to be used by anyone, these are created for the sole purpose of this study, it means that any activity that we see on these machines is bot related. And now we just have to differentiate between benign bot related or malicious bot related. So this is the overview of our system, and I'll just highlight a few components, and I'll tell you how you can read more about the system at the end of this. So we can talk about the control center. So the first question is, what applications do we deploy? If we have, ultimate freedom, what web applications would be the best bait for attackers? And so our reasoning was that we want to deploy web applications that have been around for a long time. So WordPress, Joomla, Drupal, PHPMyAdmin, and Webmin, these are the ones we selected. And these have certain specific characteristics. The first one is that in addition to being around for a long time, they have been quite vulnerable for a long time, right? A software that's been around for 10 or 20 years has had tens, if not hundreds, of historical vulnerabilities. So if you put such an application online, we know or we suspect that bots will have an arsenal of exploits for them, and they will try to fire them against them, all right? And we know that they're very popular. So an attacker will have all the reasons in the world to actually go through the process of building a bot to attack those specific web applications, right? And finally, in terms of types, we're using both CMSs as well as system administration tools, again, offering the promise of stealing user data from CMSs, but also getting some form of remote code execution through the system administration tools, right? So then we use fingerprinting. And in case you're not familiar, browser fingerprinting has been, let's say, in the news for more than 10 years. And the general idea is that you can extract attributes from a user's or from, let's say, web client's browsing environment. And once you combine all of these attributes together, you actually get something that's fairly unique, right? So if I'm able to read the list of fonts from your browser, read your screen resolution, render a complex 3D image in a canvas element and read that back as a series of bytes. So if I just combine all of this together, I will get something that is quite unique to you, right? It's not shared by anyone else. And of course, as you can see, the original problem with this was that this can be used for tracking, right? So I can track you now through fingerprinting without actually worrying about if you deleted your cookies or if you're going in and out of a private mode of your browser, right? And so academics had shown back in 2011 or 2012, I believe, that once you actually are able to extract a list of fonts, you have quite high uniqueness among the users who are being fingerprinted. And so what we did is we actually modified a popular open source fingerprinting library called FPGAS2. And we made it more modular so that we could account for partial support of JavaScript, right? Because we don't necessarily expect the bots running full JavaScript engines. Maybe they run a best effort engine. So we want to make sure that this can run for as much as possible before it breaks. So we can, if we can't get a full fingerprint, we may be able to get a partial fingerprint, right? And so once we get a client on one of our honey sites, then we can actually proceed to fingerprint them. So we can do JavaScript API support, right? So just test whether they're actually implementing any JavaScript, right? Proceed to use the browser fingerprinting that I mentioned. And then finally, this is a very cool idea that I believe we were the first to try. We tested for the support of security policies. And the idea is that if you're getting a most recent version of Firefox and the most recent version of Chrome, these are well capable, for example, of enforcing CSP, right? So if you have a CSP policy and you're observing that you try to violate it on purpose, and you observe that the current client allows you to violate it, that means that clearly that client is not enforcing that CSP policy. And if it can't be that it's the most recent version of a popular browser, therefore someone is just faking the user agent, right? And the final one, which is perhaps the one that I am the most proud of, with my students, of course, is that we can actually fingerprint the TLS handshake part of a communication. So whenever a client connects to one of our honey sites, they offer a list of cryptographic parameters. And in these cryptographic parameters, among others, they offer cipher lists. So these are the lists, the list of cipher suites that the current client can support. And so from that list, the server picks one that is the best one according to the server. And what's interesting, of course, is that different client-side TLS stacks support different cipher suites and different TLS initialization parameters. So the fingerprint, effectively, the cipher list that you will extract from a curl or wget is very, very different than the list that you will extract from Mozilla Firefox or Google Chrome. And so we use pretty much exactly that to take the fingerprints of popular browsers and popular tools and be able to differentiate among them. So you can see here that, for instance, Chrome and Chromium-based browsers support certain extensions of TLS, such as Grease, that other browsers do not support. And as I mentioned, command line tools have very different support for cipher suites than popular browsers. So if you look here at the bottom, we can have a very simple client written in Go, and we can have the fingerprint of that client that we extract from the very first request that they're sending us, right? So this is even before we start speaking HTTP to that client, we can already extract forensic information that we can then use on the fly, potentially, to say that, okay, this is not who it pretends to be, right? So now let's talk about how we deploy these honey sites online. So what we did is we actually registered 100 domains, and we made sure that these domains never existed before, because we wanted to make sure that we're not getting traffic because of residual trust effects, which is a different kind of worms. We're getting traffic because someone somehow has discovered our servers and our domains. So we spawn a server for each such domain using AWS. We place them around the world, and we get TLS certificates for them, again, to ensure that we can support as many clients as possible. And we effectively record everything and anything through this infrastructure for 7 months. Right? And so at the very high level, what we get in these 7 months, what we got rather, is 26.4 million requests and 200 gigabytes of recorded traffic. And I want to again mention that these are sites that should be getting zero traffic, right? Because they have no real clients. We never told anyone about these domains. They just exist. And because they just exist, right, they are actually getting so much traffic in the grand scheme of things. So the first thing we did is we actually wanted to understand whether traffic and the IP addresses of clients taper down. And we discovered that no, they don't, right? So if you look at the top of this graph, we actually reach a steady state of new IP addresses connecting to our honey sites each and every day. So it's not like we're going to get less and less over time. We're actually getting a stable number of IP addresses that are hitting our servers. And in terms of requests, we're actually ramping up, if you see at the bottom of this graph, rather than ramping down. And this, again, has to do with pretty much the attacks that we're attracting, right? So we're discovered one day by a given bot. It searches if we're vulnerable to something, it goes away. Then another day, we're attacked by a brute force bot that will send 1,000 requests our way, and then we get a large spike of that day, right? In terms of discovery, how is it, again, if we're not telling anyone that they're finding our honey servers or our honey sites? And what we actually discovered was that about 74% requested our pages either by directly connecting the IP address and saying nothing, or pretty much just saying that I'm trying to connect to the host that is the IP address. So this could be a generic scanning online, right, that just hit our web server, found the IP address, and then just connected to it. However, for about 30%, we are getting clients who are explicitly asking for our domains. And that is a question mark, right? How is it that someone is discovering your domain name? And based on our understanding of the world, we have the certificate transparency mechanism that potentially malicious actors are monitoring, and they're using it to discover new targets. We have zone files that are largely available to anyone who's interested in making an account. And you have prior crawls, that someone else crawled you at the time, discover your domain name, and then can attack you in the future based on that domain, right? So if we now look at the most popular targets of these bots, these are on the x-axis here on this graph. And you can see that we have different behavior. So here at the bottom, we have the most popular endpoints, and on the y-axis, we have the types of web applications. So you can see a little bit of a different pattern of requests. So there, for example, you can see that all the requests are concentrating towards a very specific web application, right? All the requests that are targeting WP admin, and I'll talk about this. Whereas in other cases, we see a more uniform distribution, where bots are just trying this URL against all of the web applications that we have deployed. And this is actually a server-side request forgery attack that these bots are trying to do based on specifics of the Amazon Web Services Cloud. So if we look at the earlier behavior, right, we see clear evidence of tailored attacks, right? You see that it's the WordPress sites that are getting the most hits for the WordPress endpoints, and it's not everyone else. So it's not like someone is just asking for WP admin from the internet. They actually first figure out that you are a WordPress site, and then they actually start attacking you, right? And so what this suggests, the implication of this, is that if you don't run multiple types of applications, you will likely have blind spots, right? You will not be able to see the traffic from bots that are targeting the web applications that you're missing, right? So now let me talk to you about some things that we expected, but it didn't turn out to be the way that we expected it to be, right? So we thought that, oh, we'll use JavaScript fingerprinting and we'll get all this information. And the truth is that we didn't, right? So as you can see here, 0.63% of the sessions on our Honey sites supported JavaScript. And fewer than those, actually, we were able to extract a full fingerprint from the client, right? So this really means that these tools are just not running JavaScript, right? They can claim to be who they want to be, but they're actually not running any JavaScript at all. The good thing about this is that you could add JavaScript as a test to your website. If you're not running JavaScript, you cannot proceed, right? And you will get rid of a large number of these generic attacking bots, right? Of course, you can have JavaScript-based bots, but you will get rid of a large chunk of the ones that are potentially attacking your website. The second thing, again, that we expected, but didn't turn out to be that way, was the honoring of robots.txt. So like others, we expected that you would have malicious bots looking at robots.txt and going to places that they shouldn't go, but that didn't turn out to be the case. We didn't see a single request. And we have certain theories about this, but I'll keep them to myself for lack of time. And then finally, we looked at shared and distributed crawling. So we had mechanisms to understand whether you have one IP address discovering links and then another pool of hosts crawling those links, as opposed to one bot doing everything. And so we discovered that this sort of distributed behavior is popular among benign bots, such as Google, but we definitely didn't see any of this in malicious bots. So the generic bots that attacked our Honey sites, they had no interest in doing any sort of distributed actions, okay? So if we talk about good bots and bad bots, right, we can try to differentiate between them and say, okay, if you're a benign bot, if we can validate your identity, if we can pin you back to a search engine or to security researchers or other companies. And if you look at the table here at the top right, you will see that we were actually able to validate the large majority of the popular search engine bots, which again means that you have very little attacks, very few attacks that change a user agent to pretend to be Googlebot, right? And most likely because of the easy methods that I showed you at the very beginning of this talk, right? In terms of malicious requests, you can see that the large chunk of requests that we got was malicious, right? They were sending unsolicited post requests towards authentication endpoints, and they were sending other requests that we were able to map to attacks, such as fingerprinting related, vulnerability scanning related, right, brute forcing, and so on. And this large chunk that's gray are bots that we just couldn't tell you what they were, right? These were typically single shot scanners. That's what we call them. They come once to your website, they ask for your page, they go away. We can trace it back to a benign entity that is well known, but they also didn't perform any attacks while they were there. So we don't know what we don't know. That's the problem with that. So let's talk a little bit about the specific attacks. So 50% of the total requests that we got were brute forcing related from 47,000 unique IP addresses. They were trying all the common passwords that you know already, right? And they also were trying the domain itself. So if you have example.com, you would have a bot trying to use example.com as a password, okay? What was interesting to us was that 99.6% of the bots, they issued fewer than 10 attempts before stopping, right? And this means that they're really after the lowest hanging fruit possible. So if your password is not in the worst possible list, right, the top 10 worst passwords, you're likely going to survive this, right? And we had actually observed the same spray and pray behavior, let's say, against SSH honeypots that we deployed 4 years ago. So then we saw reconnaissance. So we saw that applications were actually fingerprinting, clients were fingerprinting web applications. So we matched requests against databases from WhatWeb and Blind Elephant. And you can see here the popular paths that they were asking and what it is that they were trying to fingerprint at those paths, right? So again, this would be a reconnaissance step before an attack starts. And then we saw straight up exploitation attempts with old and new CVs, right? And I will show you actually some very interesting exploitation attempts in a couple of slides. We have reconnaissance that is not exploit related. Like I mentioned earlier, you're searching for misconfigurations from developers. So you're searching for backdoors, you're searching for protected files. And we saw quite a number of IP addresses that were explicitly searching for these files, trying to effectively capitalize on developer error. And we had a small number of bots, 929, that were actually doing everything, right? So these were really full-fledged attack suits that would start from reconnaissance and would just work their way through all of the attacks that they were searching for. Let me quickly tell you about TLS fingerprinting. That worked spectacularly well, unlike JavaScript fingerprinting. So we were able to actually boil down all the clients to 558 unique TLS fingerprints. And these were the real fingerprints, right? So you can see here we have tools that are built on Go, on Perl, on Python, right? Regardless of what it is that they're stating in their user agents, right? And one statistic that was interesting for us was that 86% of the connections that are connecting to us and saying, hey, I'm Firefox, hey, I'm Chrome, were in fact fake, right? They were not any of these popular browsers. They were just any of these types of tools, right? So in order to make sure I finish on time, let me just tell you about this table here, and then we'll just skip to the conclusion slide. During our 7 months, there were 5 vulnerabilities that were newly discovered and publicly disclosed. So we actually were able to discover how long it takes from publication of vulnerability to a weaponization of vulnerability. And you can see here the time, and specifically for these two, we saw requests against our honey sites that were on the same server, on the same day, excuse me, as the vulnerabilities were announced. So that means that we had pretty much 0 days between the publication of vulnerability and the very first attacks against them. So I'll skip to the conclusion because I see Martin here is giving me the look. So as we're moving more and more software to the web, right, we are also moving attackers to the web who have armies of bots available to them. And through this work, we actually showed that through very modest costs, you can build your own database of malicious bots, and you can use this database to protect your real infrastructure. You can find everything that I said plus a lot more on our paper that you can find online by just searching for the same title. And that's the end of my talk. So thank you very much.